Hey, welcome back to your favorite Fundamentals of College Math class. We're going to look at polygons, perimeters, tessellations today. Let's start out with talking about some polygons and their definition. So, polygons, any closed shape in the plane formed by three or more line segments, like a triangle or a quadrilateral. I'll show you some on the next page here. They intersect only at their endpoints. So here's some non-polygons. A circle's not a polygon. Again, you got to have three or more line segments and they got to intersect at their endpoints. Here's another one. Notice they don't meet. Uh, here's one more. They don't meet at the endpoints, right? Look at that. They're intersecting inside that line segment there. Now, a regular polygon just means that it's a polygon where all the sides are the same length. And so if all the sides are the same length, your angles are also going to be the same measure. And then the perimeter of a polygon, that's just when you add up the sum length of all the sides. If you've got like 3, 3, 2, 2, you add them all up and you got 10. That's your perimeter there. So here's some regular polygons. Here's a triangle with three sides. And again, regular means sides are all the same length as well as the angles. So this is an equilateral triangle, which means also all the angles are the same. Here's a quadrilateral of four sides, so square. Here's a pentagon, five side. Hexagon, we got six sides. Heptagon, seven sides. Octagon, stop sign. We've got eight sides to it. Here's some types of quadrilaterals. So for the four-sided polygon, a parallelogram is simply a four-sided, it's a quadrilateral in which the opposite sides are parallel. That's the requirement. Opposite sides, those are parallel. Those are parallel as well. That's your requirement to be a parallelogram. So in fact, a rectangle, I'm sorry, a rectangle as well, but a square or a rectangle, they have opposite sides, notice, that are parallel, right? A rhombus is a parallelogram, so the opposite sides are parallel, but in addition, all the sides have equal length. So a square is also a rhombus because the opposite sides are parallel and all the sides are equal in length. A rectangle is a parallelogram, so again, opposite sides parallel. And in addition, you've got four right angles. Notice the 90-degree measures for the rectangle. Okay, a square is a rectangle, so opposite sides parallel, so it's a parallelogram again. You got four right angles, and in addition, it's got the requirement that all four sides are the same. Squares also qualifies as a rhombus, as we mentioned as well. Square also qualifies as a rectangle, right? And then finally, a trapezoid. A trapezoid is a quadrilateral, and it's only got one pair of parallel sides. So notice those two sides are parallel, but these ones here are not parallel. So that's a trapezoid. Let's do an application with perimeter here. We got fencing costs $5.25 per foot. So what would it cost to enclose this field with fencing? Now notice they're giving us the cost and it's per foot, but if you notice this length here, 42, is in yards. So the first thing we got to do is I got to say, well, let's convert the 42 yards. Let's get that in feet. And we know there's 3 feet for every 1 yard. So we got 42 times 3, which ends up being 126 feet. So this is 126 feet. Because what we got to do is we got to find the perimeter here. Now we got the 28 yards up there. So 28 yards, there's 3 feet. Oh my gosh, feet. Sorry about that. Per one, that's feet right there. Per 1 yard. Yards cancel. So we got 28 times 3, which ends up giving, what is that, 84 feet? So 84 feet is your width there. So 126 length, 84 feet width. So your perimeter which is length plus width plus width, right? I'm just adding up length plus the other length plus the width plus the width. So two of those lengths and two of those widths. So we got 2 times 126 feet. We got 2 times the 84 feet. So it looks like we've got, what's that, 252 feet, 168 feet. So this whole perimeter is, what's that, 420 feet? So that's how much fencing we need. We need 420 feet of fencing. So the cost of this to fence it, since we have 420 feet all the way around, and it costs 5.25 per foot, $5.25 per foot. Notice our feet here cancel. So 420 times $5.25 ends up being $2,205 is our cost. That's our cost to fence, enclose that field with fencing. All right, the sum of the measures of a polygon's angle. So the sum of the measures of the angles of a polygon with n sides is n minus 2 times 180. And you know what? I think it's worth a discussion to talk about, kind of inductively why that is. Let's think about, if we had a three-sided polygon, so a triangle, right? Let's say we had a triangle. If we were to add up the interior angles, x plus y plus z. By Euclid's theorem, we know that those add up to 180 degrees from last time, right? Now, what if we went to a four-sided polygon? So we got some sort of quadrilateral. Say we got like a trapezoid or something. Now we want to add up all four angles inside and see what they add up to. But what I'm going to do is, since I know the interior angles of a triangle add up to 180 by Euclid's theorem, let me split this up and create two triangles. So I have XYZ that adds up to 180 and ABC. So X plus Y plus Z and A plus B plus C. And that takes care of, there's 180 degrees, there's 180 degrees. In other words, we have two of these 180 degrees, 360 degrees, right? This one I only had one of these 180 degrees. This one I had two 180 degrees, right? And I'm adding up all the interior. Notice it took care of all four of those interior angles in total, right? Let's do one more five-sided. Let's see if you can kind of see the pattern here. If I take a five-sided, let's say I've got something like this, okay? And I'm going to add up all five angles, right? I'm going to add them all up. I want to know what those are, and I'm going to do it, and I'm going to say, well, let's create triangles again. So I got X, Y, Z, A, B, C, D, E, F. So X, Y, Z, A, B, C. You know what, let me do it up here. X, Y, Z, A, B, C, and D, E, and F. So I have 180 from there, 180 from that triangle, 180 from the interior angles of that triangle. In other words, I got three of these 180 degrees. In other words, 540 degrees. Now let's see if you see the pattern. For a three-sided polygon, I had one set of 180 degrees. For a four-sided polygon, I had two sets of 180 degrees. For a five-sided polygon, I had three sets of 180 degrees. In other words, n minus 2 times 180. So if I had a six-sided polygon, then I'd have 6 goes in for n, 6 minus 2 times 180 degrees. So I'd have 4 times 180 degrees. In other words, 720 degrees is how you do that. Now for this one, it's asking us find the measures of the angles of an octagon. Well, we know an octagon's got how many sides? 8 sides. So we're just going to say, well, for a stop sign, oh my gosh, this is awful. I can't draw. All 1, 2, 3, 4, 5, 6, 7, 8. All those, if I plug 8 in, I've got 6 times 180, right? 8 minus 2 times 180, 6 times 180, or 1080 is what all 6 of those angles add up to. Okay. All right, let's move into tessellation. So a tessellation is a pattern consisting of the repeated use of the same geometric figures to completely cover a plane, leaving no gaps, no overlaps. Now, the sum of the measures of the angles that come together at each vertex is 360 degrees. We'll give you a picture of this. Now, there is a restrictive condition in creating tessellations, is it just that one type of regular polygon may be used. So let's look at here some tessellations here. You notice with these tessellations, so this, you might want to think of this is like tiling a floor, right? You don't want to leave any gaps there when you're tiling a floor. And so over here we've got an octagon here, right? Regular octagons, and then you've got squares in between them. But notice where they meet. So they meet right here, right there. That's 360 degrees. There's no gap there, right? There's no gap there. Here they meet on this other one where we've got a hexagon with a triangle. Again, they meet and it covers 360 degrees. There's no gap there. So let's think about this for a minute. Explain why a tessellation cannot be created using only regular pentagons. So the question is, if I had these regular pentagons, regular meaning all the sides are equal in length, right? These are all equal in length. Could I fit them together? I'm not drawing this very good at all. Could I fit this together and then fit one more in here, right? That's the question. They're all regular pentagons. Well, it's saying we can't do it. Well, why not? Let's see here. What would these angles be right here? Each of these angles, if I had a regular, nicely drawn pentagon. Well, I know a five-sided pentagon, the sum of their angles would be n minus 2 times 180 degrees. So 3 times 180 degrees, so 540 degrees would be the sum of all the 1, 2, 3, 4, 5, all 5. So each angle in there, each angle would be 540 divided by there's 5 of those angles. In other words, each angle is 108 degrees. So this is 108. That's 108. I know I didn't draw it very good. That's 108. The question is, does another 108 fit in perfectly right there? And I say there's no way because 108 plus 108 plus 108, right? If I had 3 of those, then I'd have 324 degrees. And it has to be 360 degrees where they meet. So I can't fit another 108 in there because now I'm going over 360, right? I'm 432 degrees. Here's a little better picture of it. I can fit 3, but I have a 36-degree gap. I can't fit in a perfect 108 degrees right in there. So I can't use pentagons to tile, if you will, right, to create this tessellation, this perfect tessellation. So that's the end of our discussion today. Thanks for listening. Take a look at your geometry and parameters, tessellations, all that stuff today. Thank you.